In section 3, we're going to look at sampling distributions when you're looking at a difference in sample proportions. So a lot of the time, you're not just looking at one sample proportion, you are comparing two portions or means, which is what we're going to talk about next, based on random sampling or a randomized experiment. So you want to determine whether the two treatments caused the observed difference, or we want to draw a conclusion about the population for all subjects. So let's look at a very common example when comparing two proportions. So if you're comparing two drugs, such as Lipitor or Pravachol, they help lower bad cholesterol. We want to know, well, which one does it better or more? So researchers used 4,000 people with heart disease as subjects. These individuals were randomly assigned to one of two treatment groups, Lipitor or Pravachol. At the end of the study, researchers compared the proportion of subjects in each group who had died, had a heart attack, or suffered other serious consequences within 2 years. So if we think back to when we were doing completely randomized designs, so we start off with our 4,000 subjects. Okay. They are randomly assigned to one of two groups, Lipitor or Pravachol. And we know that there are 2,000 people in each group. And then after 2 years, we compared the results. And the study found for those using Pravachol, the proportion of people who had died, had a heart attack, or suffered other serious consequences was 0.263. And for those using Lipitor, it was 0.224. So you want to know, could such a difference have occurred purely by chance involved in the random assignment? So what we're asking is this result due to sampling variability or because in this case it would be Lipitor is a better drug. We are going to eventually answer that question. We're going to talk about how to perform a test to determine whether or not your result is due to sampling variability or because something is better. So just to kind of look at difference in proportions. So you're going to have two different groups, your first one and your second one, however you decide to label them. You're going to have two parameters. You're going to have two test statistics, and you're going to have two sample sizes. Now, those sample sizes could be the same size, like in our last example, we had 2,000 people in each of our groups, or they could be different. Hopefully, they're not so different, like 20 and 600. They should be relatively close, like 40 and 60, relatively close, 100, 150. You don't want the sample sizes to be too different, though. So when we are looking at the shapes of sampling distributions, when we're looking at sampling distribution, we're looking at the difference P1 hat minus P2 hat. That's the typical setup. You could do it the other way, P2 hat minus P1 hat, depending on what you're trying to find probability-wise. But typically it's P1 minus P2. So for our shape, just like when we were looking at one sampling distribution, this shape should be approximately normal. Now, when we are testing that the shape of the difference is approximately normal, we're checking that each distribution is approximately normal. Because if each distribution is approximately normal, their difference will be 2. So I have to check that N1 P1 is greater than or equal to 10, and that N1 times 1 minus P1 is greater than or equal to 10. And then I have to check N2 P2 greater than or equal to 10, and N2 times 1 minus P2 is greater than or equal to 10. So I have 4 things I need to check because they both have to be approximately normal. For the center, so the mean for their difference, P1 minus P2, is going to equal just subtracting the means of our sampling distributions. Just like that example we did in the first section, we were able to subtract their means. That's how we get the mean of our sampling distribution, just subtract them. The condition here is that both distributions have random sampling or an SRS. So either you collect your sample randomly, or you assign people to a group randomly, such as an SRS. Okay, so then our spread, our standard deviation of P1 hat minus P2 hat, we're going to do P1 times 1 minus P1 all over N1 plus P2 times 1 minus P2 all over N2, all under the square root. And our condition here, so N1 has to be less than or equal to 10% of its population, and N2 has to be less than or equal to 10% of its population. Now, in the example that we first looked at, we were drawing from the same population of people who have heart disease, and our sample sizes were the same. So sometimes this condition you only have to check once, if your sample sizes are the same and you're looking at the same population. If your sample sizes are different, then you have to check the condition for both of them. So let's apply this to an example. You have 2 large bins of several thousand plastic beads. Bin A is 60% red beads, and bin B is 48% red beads. Suppose you take a random sample of 80 beads from each bin and calculate P hat A, which is the proportion of red beads in the sample from bin A, and P hat B, the proportion of red beads in the sample from bin B. So first thing we want to do is describe our sampling distribution, which basically means check your conditions. So the first thing we're going to check is random. And if we look in our problem, it says that there's a random sample of 80 beads from each bin. So we have random for bin A, and we have random for bin B. Next, we need to check independent. So that's going to be our NP greater than or equal to 10 and N times 1 minus P greater than or equal to 10. So I have to do it for bin A and bin B. So we took 80 from bin A, and the proportion is 0.60. And then we have to do 1 minus 0.60. So 60% of 80 is roughly 49 or 59 point something. So it is greater than or equal to 10. And then 80% of 1 minus 0.60, 1 minus 0.60 is 40%. 40% of 80 is, I want to say, close to 20. So we're good there. Now we need to check bin B. So 80 times 0.48 has to be greater than or equal to 10. and 80 times 1 minus 0.48 has to be greater than or equal to 10. 48% of 80 is greater than or equal to 10, and so is 52, which is what 1 minus 0.48 is. Okay. Last thing we need to check is normal. So because we took 80 beads from each sample, I'm not going to check it twice. So we're looking to see that 80 is less than or equal to 10% of all beads. Now we know from the problem that there are several thousand plastic beads in each of the large bins. And 10, if I multiply 80 by 10, I get 800, which is definitely a lot smaller than several thousand. So that condition is met as well. Now we're going to actually calculate the probability that the proportion of red beads you select from bin B is higher than the proportion of red beads you select from bin A. So we're looking at the probability that the difference of the two proportions is less than 0. So here is where you have the option of writing your sentence differently. So I looked at their difference being less than 0 because P1 hat is bin A, P2 hat is bin B. Let's actually change this back to PA and PB, which is what it says in the problem. So we're looking at the difference, and when I set it up this way, I'm looking at it less than 0. If I set it up the other way, proportion of bin B minus the proportion from bin A, then my probability statement would be greater than 0. So you have the choice here when you're looking at the difference, how to set it up, whether or not you're looking at A minus B or B minus A, which will change your mean, but it does not change the standard deviation. It changes the z-score, but the probability should be the same in the end. So the mean of our sampling distribution is going to be 0.6 minus 0.48, which gives us 0.12. Our standard deviation is 0.6 times 0.4 over 80 plus 0.48 times 0.52 all over 80 underneath the square root. And we get 0.0782. Now I'm going to calculate my z-score. So we're looking at 0 minus 0.12 over 0.0782. And we get negative 1.53. So I'm now going to go into normal CDF. Okay. Our lower bound is going to be the negative 1E99 because we're looking at less than. Our upper bound will be negative 1.53. Mean is 0, standard deviation of 1. And you should get 0.063 as your probability. So what that tells us is the probability, the proportion of red beads in bin B is greater than the proportion of red beads in bin A I ran a room, so E is 0.063. So it's not very likely that the proportion of red beads in bin B is more than bin A, which you can kind of tell from the beginning because in our sample, only 48% from bin B were red and 60% for bin A were red. So with that large of a difference, it's not likely. If they had been closer together, then we could say, it's due to sampling variability. But in this case, it's more likely that the actual proportion of red beads in bin A is larger than bin B. Let me know if you have any questions over differences in proportions.